So, let's move on. So, it's the three of you that are taking the exam.
Right after this, yeah.
You guys can sit out. Just go.
What?
Just go. Just go. You guys can leave.
Okay.
I'll spend time with the rest of them.
What?
Thank you.
Because we're not talking about anything that's needed for stuff. That's extra stuff. So.
Okay.
Like this isn't on the final or anything at all?
Probably not, no.
Okay.
So, today I want to talk about a new topic. I'm going to talk about something called improper integrals. So I was thinking about what to do today. We don't really have anything extra. I don't really have anything extra to teach. I thought it would be a good idea to do trig sub and trig integrals, make getting into Calc 2 a little bit easier. But I don't think I can do that topic justice in like one session. So partial fractions would also be another good idea, but also I don't think I can do that in one session. Improper integrals, I think I can get through 90 to 95% of what you need to know for this. So that's what we're going to do. And we'll practice a little bit of integration while doing this. It's not going to be anything too complicated. So here's a definition. The integral a to b of x dx is called improper if one of two things happen. Either you are on an infinite limit, so if your a is negative infinity or your b is positive infinity, and or two, f is undefined or discontinuous, has a bad point. Let's put discontinuous. At isolated points in so might seem crazy that we're actually considering infinity as limits here, but it turns out that considering definite integrals over infinite intervals actually has a lot of applications in sciences, engineering, mathematics, all that stuff. These guys are really important. You'll learn about it in Calc 2. You'll also apply it in many other courses depending on where you're going to go. But ultimately, we remember what this guy is. This is just a definite integral. Same guy we've been looking at for a while, but now I want to deal with a situation. What if infinity is on our limits or the function is not defined? So, example. So, integral from 1 to infinity of 1 over x is improper. Why? Because there's an infinity in the limit. It's also true that the integral from minus 1 to 1 of 1 over x is improper because x is undefined. The function 1 over x is undefined at 0, and 0 is in that interval. So this guy is improper. Because of the infinity limit. And this guy is improper. Because f of x equals 1 over x is not continuous at x equals 0, and of course 0 is in this interval. So that's an example of an improper integral. So sometimes we want to consider something on an infinite limit. It actually has a lot more application than you would think. And other times we want to consider something on a pretty typical interval. However, the function itself that we care about misbehaves on that interval, right? So if we're looking at this guy, we know that 1 over x looks like this. If we're looking at -1 to 1, between those two, there's an entire chasm here, right? So we still want to examine this function in terms of integration, but there are issues. So whenever you consider such an integral, you say you're doing an improper integral. There are a lot of tangents and paradoxes that we can talk about with these kinds of integrals, but we will skip them for sake of efficiency. So sometimes an improper integral can give a finite value. Right? Now that might be strange. For example, look at that integral. We'll actually look at it specifically later on. Equals some number. It equals c, where c is actually a finite number, believe it or not. Right? So we can actually look at this function here, which is 1 over x squared, on the interval 1 to infinity. So what we're finding is this area. That seems to be an infinite area, except it's not. Right? And strange things like that can actually happen. Turns out that if you actually find the area of under 1 over x squared on the interval 1 to infinity, you actually get a finite number, even though the function never actually closes off at any point. Okay? So strange things like that can happen, and when this happens, let's call it C. When this happens, we say the integral converges to C. So we say this is an improper integral, but it converges to a certain value. Converges is actually pretty specific language here, because that's how we would compute one. How do we compute improper integrals? In order to be consistent with calculus as we know it, right? How do you actually deal with such a situation where your function misbehaves on an interval, has a gap or a hole or a break, or goes on forever, and you still want to actually integrate it? Well, the idea here is to use limits to approach the bad points. Not a technical term, I just call them bad points. So a bad point is, it's either plus or minus infinity, or points where the function is undefined. So we might be talking about some function, f, doing its thing, has a hole here, doing its thing. I want to integrate along A, B, which means I need to find the area under this curve. Except the curve does not exist at this location. Right? So let's say that's C. So I want to actually find the area under this curve. Now it turns out, if this is actually a single point, that means that the function has no value along this line. But it also turns out that the width of a line is nothing, right? A line has no width. So technically, this line being missing doesn't actually subtract from the area. It's actually a situation where you can kind of ignore the fact that the function doesn't work there. However, you can't always ignore the fact, so what you do to make sure whether or not you can ignore the fact is you approach C with a limit, right? So you take the limit as x approaches C from the left, and you take the limit as x approaches C from the right of your integral function. So you might have a situation like this, where it seems obvious to us that we can actually compute the area and not worry about the point where the function is undefined. It's not always the case though. There are times when we do have to worry about how the function would behave. For example, if there's an asymptote, that might be a very big issue. But how we actually deal with that situation is, if that's a bad point, the function is undefined, I can't actually plug in C, the next best thing is to get as close to C as possible and figure out what's happening. So we use limits. So that's how we compute it. But we do it very carefully. The caveat here is you can only have one bad point per integral. And so this leads us to the strategy is to, one, expose the bad points if they aren't already. 2, we have theorems that tell us that we can break up the integral. Three, set limits to approach the bad points. And 4, you pretty much otherwise compute the integrals as you usually would. Let's actually do some examples. Yeah. Skipping the intro on the pleasantries, there are a lot of really cool things we can talk about when talking about improper integrals, but I just want you guys to know how you actually compute them. We're getting to the meat and potatoes of the computations here. That's an improper integral, pretty obvious because of the infinite limit here. That's also an improper integral because it's undefined at x equals 0 and 0 is on the interval that we're integrating. Similarly here, so 0 to infinity of 1 over 1 plus x squared dx. Also, I'll do an e. guess we can put a 5 here. All your limits, because you might have several of them in play, all your limits must be finite for convergence to occur. Otherwise, we would say it diverges. So, show you an example. So we know x equals 0 is bad news, but we're actually on the interval from 1 to infinity. So we start at 1 and we are going onwards. 0 is a bad point, but it's not in our interval of consideration, so we don't have to worry about it. The infinity is the issue though. So what you do is we're going to set up a limit to approach infinity. And say the limit as say n approaches infinity, and I'm going to do the integral from 1 up to n. So I'm just finding the area and then pushing it a little more, a little more, a little more, a little more, keep finding areas. Now, at the moment, ignore the limit. You're just going to compute this integral as you would with the fundamental theorem of calculus, as you usually do it. So the limit just keeps coming along for the ride. To integrate this, you'd obviously use the power rule here, write that as x to the minus 2. Integrate that, you get minus 1 over x between 1 and n. Now, you plug in n. Minus, you plug in 1. And so now you take the limit. What is the limit of 1 over n as n goes to infinity?
0.
0. So this ends up being minus 1 times minus 1. You actually get 1 as the answer. This converges. In other words, what I'm saying is if you look under the graph, y equals 1 over x squared, that's just the right side, there's another side here. And you start at 1, and you measure the area going off to infinity, the area is actually 1. It's a finite number. Kind of weird, but being able to talk about things like that has a lot of applications. Really, I can't explain at this point how useful it is knowing that we can actually compute things like this and actually get finite values. What about this one? B. Same function, I change the interval. This interval goes from 0 to 1. But obviously, 0 is bad news because 1 over x squared is undefined at 0. You end up with a division by 0 there. So, obviously, since we're on this interval here, we want to approach 0 from this side, so I'm going to take the limit as we approach 0 from the left, from the right of our integral. So, what I do here, take the limit as n approaches 0 from the right, putting n in 1. Again, compute it just as usual. This here is, we already saw it's minus 1 over x between n and 1. That's going to be the limit as n approaches 0 from the right of plug in 1, get minus 1, minus plug in n, minus 1 over n And now the question is, as we approach 0 from the right of 1 over n, that will actually give us infinity, right? Think of the graph 1 over x. As you approach 0 from the right, it shoots up to infinity. So this gives us minus 1 plus infinity. This diverges to infinity. And that's how we say it. We'd say it diverges. Specifically, it diverges to positive infinity, right? So this one doesn't actually give us an answer. So it turns out, again, looking at the same graph, if I were to find the area from 1 all the way to infinity, it's actually just 1. However, if I consider the question, let's find the area here as that goes up to infinity, turns out that that area is infinity. There's infinite area between 0 and 1. But only finite area from 1 to forever. So among other things, this kind of illustrates how much of a big deal division by 0 is. So in that syllabus, when I told you, you can't divide by 0 and calculus, it's a very serious problem. Like, you can't even save it with a limit a lot of the times. So that one diverges. This integral has no meaningful value for us. But from 1 to infinity, it did. And it kind of stands to reason that this one is also going to be a problem, because this includes the 0. But I want to show you, if we pretend we didn't know parts A and B, how would you deal with this guy? What I want you to notice here is that both 0 and infinity are quote-unquote bad points. Infinity is not an actual number that you can plug into your function, so it's not defined. And obviously you can't plug in 0. So I have 2 bad points on the integral. The rules say I should try to get to a situation where I only deal with 1 bad point at a time. And we can do that by simply splitting up the integral. So I can go from 0 to some number plus that number up to infinity. We know we can do this with integrals. This was in the properties 2 or 3 lectures ago. We spoke about that. And in general, you can pick any number you want here. But let's just put 1 just for definiteness sake. So now I can split this integral up into a situation where I have bad points. There are only 2 of them, but I split it up into a situation where I only have 1 at a time to worry about. What you would do at this point is you want to do each of these bad points separately. So you'll set up a separate limit for each of them. So let n go off to 0 from the right, integrating from n up to 1. Plus the limit, let's measure this with a new guy, call it m. m goes off to infinity from 1 to m. So what does it mean to go up to infinity? Just stop at a value, but keep pushing that value further and further. Now, we already saw that this guy actually came up to a number. So you can actually find a value there by following the previous steps. But this one came down to infinity if you follow the steps from B. So now we have a situation where we have infinity plus 1. Well, that diverges. So is one of the reasons why all the limits have to actually converge in order for you to have an answer. Because if one part of your interval behaves but the other part doesn't, it doesn't matter. Like this could be any number it wants. Once this guy goes off to infinity or negative infinity, it doesn't matter what that number is. So all our limits have to converge to finite values for us to consider convergence an actual thing. So this tells me, of course, looking at this graph, from 0 to infinity, the area diverges. Now if I were to cut off a part of it from 1 onwards, that's actually a finite portion. The infinite portion is over here. So let's consider the area under that graph on 0 to infinity. Now this is 1 over 1 plus x squared. This guy kind of looks like this. Never actually touches the x-axis. The max value is actually 1. But I want the area of half of this guy. So 1 over 1 plus x squared is actually never undefined. That's continuous for all x values, right? You never divide by 0. 1 plus x squared is never 0. So the function itself doesn't misbehave, which makes the only bad point here is actually infinity, because that's not actually a number we can technically plug in. So simply take a limit. And do you remember what the integral of 1 over 1 plus x squared is?
Tan inverse.
Tan inverse. So we can plug in the n, minus you plug in 0. Tan inverse of 0 is what? It's also 0. And so ultimately here what we have is we need the limit as n approaches infinity of tan inverse of n. Do you remember what that is?
Something that has to do with pi.
It's pi over 2.
Yeah.
So that actually gives us a finite value. So the tan inverse graph, remember, maximum value is pi over 2, minimum value is minus pi over 2. It goes like that. So that also has a finite area. So when does this thing actually give us a value? Now this integral is actually pretty important, and you won't need to go far to see why that's important, like in Calc 2. When you start covering series, you're going to see why this integral is actually pretty important. Actually gives us a lot of information. It's a very useful integral for all sorts of applications, which you'll see as early as Calc 2. When we talk about something called a P-series, this is one of the guys we can use to help us figure out how those guys behave. So P here I'm just considering to be a real number. So I just want to know, when does this integral converge depending on what value of P I pick? Now, of course, we're on 1 to infinity, so 1 over x is going to be defined as long as the infinite part works out, because x equals 0 is a problem, but we don't have to worry about that on this interval. So that's the issue. So this is going to be equal to the limit as n approaches infinity, 1 up to n of 1 over x to p. This guy automatically breaks up into cases though, because how you integrate 1 over x to the p would depend on the p value. We know the integral of 1 over x is ln of absolute value of x. However, for any other p, we use the power rule. So basically, we care about if p is not equal to 1 versus if p is 1. And this I would break into several pieces as well. We can worry about what if p is positive, so like larger than 1, what if p is smaller than 1, and what if p is 1. So we have 3 cases. So at 1 we have a completely different situation, because we get ln, but otherwise we get we can use the power rule. And I'm starting to split these guys up because I can realize that, you know, if p becomes a negative number, I can flip it and it's not a fraction anymore, and issues like that. So we can also worry about those kinds of issues. Let's worry about the p is larger than 1. So if p is larger than 1, call this I, then I would be equal to the limit as n approaches infinity of 1 up to n. Of course, x to the minus p dx. And p is larger than 1, I'd actually apply the power rule here. This is the limit as x approaches infinity of you add 1 to the power and divide by the new power. I can plug in n for x. And plug in 1 for x. Now, because p is larger than 1, minus p plus 1 will give me a negative value. So I can think of this as like 1 over n to some power. And so as n goes to infinity, this part is going to go to 0, and that will actually converge. This number makes sense because my p is not 1. So in this case, we converge. What about p equals to 1? Well, if p equals to 1, well, our I is going to be the limit as n approaches infinity of 1 up to n of 1 over x dx. Integrate that. We would get ln of absolute value of x between 1 and n. This is going to be ln of n minus ln of 1, which of course goes to 0. So we're only worrying about this As n goes to infinity, the logarithm will also go to infinity. This diverges. So at 1 it diverges. For bigger than 1 it converges. What about less than 1? P is less than 1. Then our integral is going to be the limit as n approaches infinity. Of course, if it's not 1, I would use the power rule, so I'll just write it like this. This is the limit as n approaches infinity of, again, minus p plus 1 over 1 minus p, p1 and n. So this becomes n to the minus p plus 1 over 1 minus p minus 1 over 1 minus p. Now, because my p is less than 1, that makes this guy a positive number. So my n is going to infinity, and I'm raising that to a positive number. That's going to go off to infinity. So it diverges here. This leads us to a very important statement. In fact, a lot of textbooks consider it a theorem. The integral 1 to infinity of 1 over x to the p dx converges if and only if your p is larger than 1. So as long as your p is larger than 1, that guy will actually give you a finite answer. If your p is not larger than 1, it will diverge. So that's a very important thing. A very big reason why that's important is because of another idea. There's something called the comparison theorem. It allows us to figure out certain integrals by comparing them to other integrals. Again, using properties that I mentioned 2 or 3 classes ago. It says the following. Suppose we have functions g of x less than equal to f of x. Let's make them positive just to not have to worry about some certain issues. Then we would have if I take their integrals, we already saw that integrals maintain inequalities. So if I integrate everyone, they will actually maintain the order of inequalities. I want to integrate a particular thing though. I want to integrate on an infinite interval, starting from some position a all the way up to infinity. So this is true on the interval a to infinity, provided these integrals exist. So that's nothing new. That's something actually we knew 3 classes ago. Here is the important part of the theorem. I can talk about one of them by talking about the other in this particular sense. If this guy diverges, then so does the other one. And 2, if this one converges, then so does the other one. The order matters here. So these guys are both positive, which means they're either going to give me a positive number or positive infinity. What we're saying is, if this guy shoots off to infinity, then that guy also has to shoot off to infinity because he always has to be bigger, right? Conversely, if this guy stops at a finite value, this guy also has to stop at a finite value because he always has to be less, right? So this is a comparison theorem. I can talk about one of these integrals if I know something particular about the other. Knowing that this diverges, I automatically know that that diverges. And knowing that this converges, I automatically know that that converges as well. And the nice thing about that is sometimes you can do this so that one of these integrals you know very well. For example, this guy happens to be very often useful here. So throwing this guy in a situation like here where the p is less than 1, you would get that whatever this guy is, as long as it's bigger than 1 over x to the p, it's going to shoot off to infinity. And if I throw that guy over here where the p is greater than 1, then whatever this guy is, as long as he's less than 1 over x to the p, he's going to converge, right? And so we can know about certain simple integrals, and we can use those to figure out more complicated ones. And we can do that in this particular scenario, and it's called the comparison theorem when we're using this particular scenario. Example. Sometimes you come up with an integral. Maybe whatever you're studying in whatever context, this guy pops up. Now, that guy is very problematic because it has no antiderivative. Again, something you'll learn later, I guess. But yeah, using all the rules, you can throw whatever you want at it, substitution, integration by parts, some other technique. You won't be able to find an antiderivative for this guy. So this integral might be important to you for whatever reason, but you can't really compute it. First, second of all, you don't actually know if it's actually worth your time trying to approximate it. There will be ways you can approximate it, because it might just go off to infinity. So you'll put in a lot of hours of work here trying to figure out what this guy's going to converge to, and it doesn't converge. So sometimes before actually going down that rabbit hole, you want to know, is there a hope of an answer being possible? And it turns out something like the comparison theorem can show us that the answer is indeed yes. You will notice here, everyone is squared, so that's definitely positive, greater than or equal to 0. It'll be 0 when the cosine is 0, but otherwise it's going to be larger. Another thing you can note is that your cosine squared is always less than or equal to 1. Right? And of course, goes without saying it's greater than or equal to 0. So this ultimately means that this integral that I care about is actually less than or equal to that integral. Because cosine squared is always less than 1, so this expression is always less than that expression, less than or equal to. And it turns out we know about this expression. We know this converges. But you probably, let's say you didn't actually know this converges, you could actually take this a little bit further. If we didn't, or let's say you never actually worked out that this actually converges, you can actually make this guy less than someone else. Because when you make the denominator of a fraction smaller, the fraction gets larger. And this guy has the form 1 over x to the p, where your p is 2, but that's bigger than 1. So the theorem tells us this converges. Right? So I have a couple ways of finding integrals larger than this guy that definitely converge, give us a finite answer. And so we can conclude that this integral, whatever it's going to look like, if I can compute it, it will definitely give me an answer that's meaningful. It's definitely going to give me something, it's something worth searching for. So if I can't compute it exactly, I'll definitely want to try to approximate it. And if this were an integral where approximating it takes a lot of computing power, right, it's worth just doing it, right, if it's very important for us to find it. So this means by a comparison theorem. This guy, whatever it is, converges. So we can actually talk about the value of an integral, if such a value exists, without actually doing the integral. So there'll be a bunch of guys that you can compute like this for the sole purpose of, they're the ones we can calculate easy, and it's very nice that we can do it because we can use them to talk about other people that are more complicated. And we can stop there. That was, this is a topic you'll go over in Calc 2. We did it, the quick and dirty version. But at the end of the day, what you'd expect to be able to do on a test in Calc 2 would be what I showed you. But there's a lot of interesting things you can talk about here. We'll stop there. I will see you guys in a week for the final, which, as I told Julia, I'll post a mock final, but I won't post the answers. You guys have to figure that out on your own. And us.
1:30 or